We'll be looking at the exam practice question for Lewis structures and vsepr analysis. So in order to answer the short answer questions, we're going to have to figure out CS2 and PCL3. So starting off, we're going to do the balance electrons. So C is going to have 4 valence electrons. S is going to have 6. There's a 2 by the S, so we're going to have 2 of sulfur. Then we're going to add them together. 4 plus 12 is going to get us 16. And then we're going to draw it out. C is going to go in the middle, can form the most bonds. Each S will go on each side. Now that we've created the bonds, we will subtract it from the count. We're going to have 12 valence electrons over, and we're going to fill them in. And I will always recommend to start off on the outside first, and then work your way in so you can keep track of all of the electrons that you have used. Alright, so we're going to go minus 12. Well, we get 0. Now, looking at this, S follows the octet rule. Right, we've got 1, 2, 3, and 4. Alright, all adds up to 8 valence electrons. And same for the other side. But we're not done. C does not have enough. So in order to satisfy the rule, we're going to have to borrow from each side. So it'll look something like this. Form 2 bonds on each side. And for the proper way for the valence electrons, they will be diagonal across from each other. Alright, so now everything is met its rule, right? 2, 4, 6, 8. 2, 4, 6, 8. Everybody's happy. Alright, another way to check this, we can check the formal charges if we want. So 6 here, or S, is going to be 6. We have 2 bonds, and we have 4 free lone pairs. Oh. Alright, so this should come out to 0. Okay, it should be the same for both sides. C in the middle has 4 with, let's see, 1, 2, 3, 4 bonding pairs. That'll be 4, and it doesn't have any free lone pairs. So we're going to have minus 0. Our formal charges should be 0 all across. This is a happy structure. Alright, one thing to count is the electron groups. So if we count them, we have 1, 2 electron groups. So we're going to have 2 electron groups, and we're going to count it out. Alright, so we have 2 electron groups. We have 2 bonding pairs. Alright, and we don't have any lone pairs. So this will be 2. Geometry will be linear. The molecular geometry will also be linear. And because we have symmetry on both sides, we're equally pulled across the middle, right? It is non-polar. So we will be at 180 degrees. So 180 will be the answer there. We're now moving over to PCl3. Again, I like to write it out to keep track. We have P5, and we have Cl, which is 7 valence electrons, and we have 3 of them. And then we're going to add them together. 5 plus 21, and this is going to give us 26 valence electrons. So now we're going to add them all together, or we're going to put the P first, right? P can form the most bonds. And then we're going to create all of the bonds with Cl. Now that we've done that, we've used 3 bonds, so we're going to do -6 valence electrons. Then we're going to start adding them all in. Alright, we like to work from the outside in. It's going to be your best friend. Alright, now that we've done that, we've used 6 on each one. 6 times 3. We're going to have 18. Then we're going to minus it by 2. Everything is following the octet rule except for P, and we have 2 valence electrons over. So we're going to be putting 2, I can write it here, 2 valence electrons there in the middle. Alright, draw a little circle. Alright, now looking at the rule, we have 1, 2, 3, 4 electron groups. So we're going to add that in. We have 4. We're going to keep count. And then we have 3 bonding pairs. 1, 2, 3. Alright, let's write that in. 3 bonding pairs. And then we have 1 solo. So we're going to have a 1 here. So now 4 is going to be tetrahedral. And then now we're going to have 3. So we're going down the chart. We will be looking at triagonal planar. I'm sorry, triagonal pyramidal. Okay, we know tetrahedrals normally at 109.5, so because we're a little less, we'll be at 109.5, less than 109.5. And to illustrate that, we're going to have P, then we're going to have different structures here, right? That's the best way to look at it. And we have our 2 little lone pairs here. So we can see on our SCS, right, we're going to be, we have symmetry, right? Symmetry, right? Everything's equal. Everything's pulling equally against each other. So we're going to be non-polar there. However, with our CLP, we have, oh, let's fix this. We have this lone pair at top. So the CLs are equal in symmetry, but the P has that one lone pair up there. So that is, we know, is going to be polar. Just based off of the geometry, we're going to have polar. So, looking down at the next question, one of the above molecules, CS2PCl3, is polar and the other is nonpolar. Which is polar, which is nonpolar? Explain how you know which one, which is which. Use our electron groups and geometries to help you explain. So you can see, I can write this S, let's start with C. CS2 is symmetrical with no lone pairs and forms a linear geometry. Okay. And we're going to erase this to make some room. We want a quick note, so write it down. Right. Now, PCl3 has one lone pair write this one lone pair and is asymmetrical based on geometry. Right. We can obviously see that, right? You may want to add in more words. I'm just doing a quick little explanation. You can see that it's lacking the symmetry there. User electron groups and to help you explain. Alright, I think we've done that. One lone pair. It is asymmetrical. Okay. Alright. So we'll move on to the next question. Alright, see if this will work. Let's save this for now. Okay, we're still recording. Alright, so then off to the next two. On the screen right. So, based off of what we learned before, we know that non-polar can only be a dispersion factor, right? Or dispersion factor, dispersion pole. But we know all polar molecules have dispersion and their dipole as their strongest, right? Is going to be the strongest intermolecular force. Okay, so B wants us to answer, list all of the forces present in each molecule. So in CS2, this will be dispersion. And then PLC3 will be dispersion and dipole. Okay. Based on the above listed molecular forces, which molecule would you expect to have the higher the boiling point? So, this one, atoms that have low intermolecular forces have weak attractions, weak bonds. This is also going to be a covalent bond. It's non-ionic, right? So this is pretty easy to break apart with heat. And each of these values is going to show S just going to have an En value of 2.58, and C is going to have a value of 2.55. Now, looking at the chart, I believe it was coming across here. We have our 0, we have our 0.5, and I believe it was 1.5 to 2. We know that if we have not passed the 0.5 mark, we're going to be non-polar. If we're going past the 0.5, we'll be hitting polar. Right. Now with intermolecular forces and boiling point, because there's not much holding the S and C together, this will break apart pretty easily with a little bit of heat. Right. Now, a stronger intermolecular force is going to be the PCl3. Right. PCl3 is going to have dipole force, and this can be shown by the attraction dipole because it has a stronger bond that will take more energy to move atoms apart. Now, both of these are correct. My wording may not be perfect, but you get the general idea. I'm probably going to be going with this. I may get a little bit better on the wording, but I hope this helps. Right? The higher the bonding, the harder it is to separate them. The forces are stronger. The intermolecular forces are stronger in your dipoles versus your dispersion. So I want you to keep that in mind. Your hydrogen is going to be your next highest, and then your ionic bonds are your strongest. Those ones have the highest En energy. But I hope this helps.